All right, good afternoon, everyone. So can someone please confirm if you can hear me? Okay, I got a confirmation. Thank you very much. All right. Before we start, any questions from the last time? Any questions from previous lectures? None? All right, so we'll start now. So this is lecture number 17. In IC242 Continuum Mechanics, and today we'll be talking about the maximum and minimum stress values, particularly how to find the stress directions corresponding to a given sigma n comma sigma s, which is a point on the stress plane. After finishing that discussion, we'll talk about plane stresses, which are special cases in which one of the eigenvalues or principal values is 0, and it occurs quite frequently in many physical situations. Then we'll talk about spherical and deviatoric parts of stresses. So it's a very common it's a very common practice to split the stress tensor into two parts. The first one called spherical, and the second one called deviatoric. And then finally, we'll talk about the octahedral shear stresses, which again are very common in the discussion in continuum mechanics. There's just one reminder as an announcement. So I've asked you guys to please fill in a feedback form on Moodle, because I need some feedback from your side as to if you can access the material or not. I've only got around 10 votes, and I'll hope that more people will send their votes in the future. All right, so let's start. So in the previous lecture, we talked about using Mohr's circles, which are the circles which give us the information about the feasible stress space in the stress plane. So let's quickly draw the Mohr circles again. So on the x-axis, we have the normal stress, that is sigma n, and on the y-axis, we have the shear stress, or sigma s. And upon finding the three eigenvalues, which we call as sigma 1, which is the greatest eigenvalue, sigma 2, which is the next one, and sigma 3, which is the smallest eigenvalue or the principal value of the stress tensor sigma. So we call them sigma 1, sigma 2, and sigma 3. So what we do is we plot these three values. I mean, they can very well be negative. So it's not an issue. So the smallest one, sigma 3, let's say is negative in this case. So what we discussed last time was that we have, upon doing some analysis of the equations of the equations for the three normals in terms which were written in terms of our principal stresses as well as sigma s and sigma n, we found that the equations are of the feasible stress space are circles. So we had drawn three more circles. We'll only draw the top half because the bottom half does not tell us anything new. So we have C1, C2, and C3 as the three Mohr's circles. Right. So the feasible stress region, as we had shown earlier, is this region. So what that basically means is that if at point P in my physical space, which is you have the point P, and at point P you can draw a normal n hat. Now the n hat, which is a normal here, can take any direction. So the whole idea, the whole exercise here is to be able to find the sigma n comma sigma s value, which corresponds to a stress vector or attraction vector for the corresponding n hat values, and find the locus of all those sigma n comma sigma s points in the stress plane on the left hand side. So when we do that, we get this red shaded region. So as we move along, as we move around the normal along different directions, then we get the feasible stress region, which is the red shaded region on the stress plane, sigma n comma sigma s plane. So now the idea was that we can use the Mohr circles to find the maximum and the minimum sigma n and sigma s values. But there's more information contained in the Mohr circles than just that. So, any point in the feasible stress region corresponds to a given normal. So what I mean is that if I take some random point in this feasible stress region and I call that point A, then that point A corresponds to a given normal direction in my physical plane. So I call this my physical plane, and on the left hand side I call my stress plane. So stress plane is that plane where I draw the feasible stress region in sigma n comma sigma s plane, and the physical plane is which is the physical plane where the point P actually exists, and we draw the normals or the corresponding cutting planes to that normal. Okay, we are not drawing the cutting planes anymore, but I believe that we've discussed it enough number of times. You understand that a normal actually refers to a cutting plane which is splitting the body into two parts, and the cutting plane is drawn at through point P. Okay. So any point, point A, for example, in this case, any point in the feasible stress region corresponds to a given normal in the physical plane. So this point A corresponds to some normal in the physical plane. Now the exercise here is to be able to find that normal if I give you some point in the Mohr circles. Now the exercise is simply an act of geometry, nothing else. Okay, so we will quickly go through it today, but we won't spend too much time because it's a simple geometrical problem that you can solve it by yourself given enough time to understand it. So the book very well discusses geometrical ideas. So if something is not clear in this lecture that we discuss here today, please refer to the book, which is Mace and Mace, second edition. All right, so let's see if you can try to understand how to find the normal directions given point. So I would want my Mohr circles to be available when I make this discussion. So what I'll do is I'll just copy this. All right. So let's label these points to make our lives a bit easier. So we will call these points as, this point we'll call as point A, small a. This one we'll call small b, and this one we'll call small c. Now similarly, we would want to see the physical plane as well. So this is our stress plane. We'd also want to see the physical plane. So let's draw that here. Now, the way I'll draw the physical plane is instead of choosing any arbitrary Cartesian coordinate system, I'll choose the principal coordinate system. So that is to say that I'll use the starred coordinate system. Okay. So x1 star is the direction which corresponds to the principal direction or the eigen direction in the n1 hat direction. So basically our sigma 1, which is one of the eigenvalues, if I find the corresponding eigen direction, that comes out to be x1. Similarly, if I take sigma 2, which is my second eigenvalue, then the corresponding eigen direction I have is x2. And the same is true for sigma 3. Okay, so these are my eigen directions. As we discussed earlier, it's called the principal coordinate system. So I'll be working in the principal coordinate system for the next for this discussion, because as you'll see that choosing the principal coordinate system makes our lives very, very easy. All right, so let's see what happens at point A. So this point small a that we have here, let's try to understand what that small a, I mean, what that small a corresponds to in terms of the normal vector. So this small a is a point which corresponds to my eigenvalue sigma 1. Now what that means is that my cutting plane that I would have chosen is actually in this direction. Right? Because if I had chosen my cutting plane in such a way which had a normal in 1, then the corresponding, I mean, if I try to find the stress vector for this cutting plane, I would get the stress vector as having a normal component of sigma 1 and a shear component of 0, because this is your eigen direction or principal direction. Okay, so point A corresponds to this normal. So point A is a point in the feasible stress region because it falls as a boundary of the red shaded region. Okay. Now similarly, point B, which is this point B. Now this point B corresponds to sigma 2. So if I mean this point B actually has coordinates sigma 2 comma 0. So point B has coordinates sigma 2 comma 0. That is, it has it corresponds to the normal in 2, right? Because it corresponds to my principal direction in 2. Now, similarly, point C, which has coordinates sigma 3 comma 0, corresponds to in 3. Yeah, and that's obvious because we're talking about the eigen directions. In eigen directions, we have only normal stresses, no shear stresses. So any point on the x-axis of the stress plane, which is on the sigma n axis, corresponds to an eigen direction. And we only have 3 points, A, B, and C, in the feasible stress region, which fall on the sigma n axis. Now remember, feasible stress region is the red shaded region. Okay? So the red shaded region intersects the sigma n axis at only 3 points, A, B, and C. Now, what we usually do, because we have to figure out the normal direction, it's easier if we draw the first octant of a sphere centered at point P. So what I mean is, I will quickly erase these normal directions just for clarity. So if you try to imagine, if I draw a sphere centered at point P and take only the first octant of that, then I get this black region that I've drawn. Okay, so that's 1/8 of the sphere centered around point P. Now, this sphere does not mean anything physically. The reason we are doing this is to be able to find the normal direction. So what I mean is that now any normal that I draw centered at point P, the way we have been drawing, will intersect the first octant at some point. Okay, so let's see how that works. Okay, so there's a question by one of the students. I'll finish this discussion that I'm doing right now, and then I'll go back to the question. So if I draw any normal, any arbitrary normal, so any arbitrary normal will intersect the sphere, so that the dashed line is inside the sphere and the solid line is outside the sphere, and the point of intersection I've denoted by this cross x. Okay, so it pierces out through the sphere at the point x, at the cross, and comes out as a normal n hat. Okay, so this is an arbitrary normal, and that arbitrary normal will correspond to some point on the stress plane. So I don't mean this point A anymore, so I'll remove that. Okay. So now let's go back to our points small a, small b, and small c. So if I take my point small a, then that will correspond to point capital A, which is this one. Okay. So what that means is that, I mean, now we'll denote the normals as capital points piercing out to the sphere or cutting the sphere at certain points. So a normal for small a, which is this one, corresponds to the capital A point which pierces out from the sphere surface. Similarly, small b, which corresponds to sigma 2, the principal stress sigma 2 will be correspond to capital B here, and the point C will correspond to the point capital C, which is on the X3 star axis. Okay. Now, if I were to move on my circle number 1, which is this circle. So if I was moving on circle number 1, so what that means is if I go from point small a to point small b on the surface of the circle, because the surface of the circle also lies on the feasible stress region. So what I'll see is that I will move in my principal plane from point capital A to point capital B, right? Because when I stay on the circle C1 here, then that basically means is that I'm always my X3 star, or I'm moving in a plane in the physical plane, which is in a plane perpendicular to X3 star. Okay, so any point on circle C1 corresponds to a normal which is at 90 degrees to the X3 star plane. Similarly, if I move on circle number 2, which is this one, then moving on circle number 2 from point small b to small c, will correspond to a movement from point capital B to point capital C in the physical plane. So moving from point capital B to capital C basically means the normal is always perpendicular to x1 star axis. Okay. All right. So that sort of gives us an idea as to what the points on the circle are, and similarly the same is true for circle number C. So I won't repeat that. Now let's look at the angles. So when I moved on circle number 1, C1, from point small a to point small b, then I moved an angle of 180 degrees. So when I say that I moved from point A to point B, then I moved some theta, and that theta went from 0 to 180 degrees. So I moved a total of 180 degrees when I moved from point small a to point small b. But in the physical plane, my movement of the normal only happened only happened 90 degrees. Okay, so what that means is that, so let's call this so we'll call this theta sigma. That's the angle in the stress plane, and this angle we'll call theta physical. It's a bit cluttered, the figure right now, but I assume you get the idea. All right. Okay, so now the question, let's look at the question. Somebody had a question. So the question is, in this case, is sigma n min 0 or sigma 3 as it is negative? Does it only mean change in direction? Yeah, so it's a very good question. What is the meaning of sigma n directions? Sigma n being positive or negative? So sigma n, when it is negative, that means it's a compressive stress. Okay? Because remember, when we used to draw the components of the stress vector at a given normal and a given cutting plane, then well, let's do that. So if you have surface point P and a cutting plane, so when we considered only the first part, the first half, then we used to draw the outward normal n hat and a stress vector t n hat. So the component of the stress vector in the direction of n hat is my sigma n. That is this one. So sigma n being positive means it's a tensile stress. It's just pulling it out. And sigma n being negative means it's a compressive stress. That's, in that case, this T would be something like this. So it will have a component which is on the inside. It's compressing the body. It's pushing it in. Okay, so sigma n being negative means it's a compressive stress. Okay. All right. So now we have we have talked about staying on the boundaries, but what if our normal n is actually somewhere on the inside? That means the case that we have here. So our normal is actually piercing the body, piercing the first octant of the sphere at some arbitrary point. So that would correspond to some arbitrary point on the stress plane. Here. So how do we find that? Again, as I said, it's a purely geometrical exercise. You can do it quite easily, but let's get a motivation as to how we proceed. So the idea is that you find the direction cosines of the normal n hat. So what I mean is you find the angle it makes with the three principal directions, x1 star, x2 star, and x3 star. So what you do is, let's say the angle n hat makes with x1 star is phi. So we call this angle phi. So that's the angle n hat makes with the x1 star direction. Similarly, the angle n hat makes with x2 star, we'll call it beta. And the angle it makes with the x3 star direction, we'll call it theta. So I can write my n hat vector as you can write n hat as cos phi e1 star e3 star. So what we do is we try to find intersection points. By finding the way you do in geometry, you try to make two arcs and try to find intersection points, and that will give you the point corresponding to this arbitrary point and the n hat normal. So our point here is the figures got a bit cluttered, so we'll clean it a bit. I assume you understand what the three angles are. It's phi, beta, and theta. So this point that I had drawn with a circle here, I'll call it point small q, and that corresponds to this intersection point capital Q, because that's the normal we're talking about. So what you do is you keep one of the angles constant. So what you do is you keep the angle phi constant to start with. So you move in this on this curved surface, keeping the angle phi constant. So what that means is the point of intersection of this black offset curve, we'll call that K here, and the other one, the point of intersection, we'll call that point D here. So point K makes an angle of phi with A. So this angle is phi, and point D also makes an angle of phi. So what that means is I keep one of the angles constant. So I move in on the surface of this first octant sphere in such a way so that one of the angles is constant. So I go from my K to D. Now, if you remember that point D, which lies on the curve AB, falls on the circle number 1, which is C1. And as you can see that D is very close to B, so D is somewhat close to point small b. So I will draw that here. So I'm just giving you geometrical ideas. I mean, I'm not talking about this rigorously, but it just gets you started. So if you really want to go through it, then you can read the book in more detail. So my capital D corresponds to the small d here, and then my capital K, which is on the AC physical plane, AC curve, which corresponds to my circle number C3, which is this one. Okay, so it is somewhere near point C. Let's call this point K. And then you can also form a plane. I mean, you can keep one of the other angles constant. So let's say you keep the angle that it makes with x2 star, that's beta. You keep the beta constant, then you get this green curve, which goes from some point on, again, AB to some point on BC. And then the point on AB then again will lie on your circle AB. So here, and the second point will lie on your BC, which is your circle number C2 here. So then I'm not drawing it very well, but the intersection of this black one and the green one it definitely has to lie in the feasible stress region. Okay, so somewhere here is that point Q. Right. So that's pretty much the idea that you use. So the whole idea here was to convey the message that more circles give us more information than just giving us the maximum shear stress and maximum normal stress values. So the maximum shear any point in the feasible stress region in the Mohr circles corresponds to some point, so some point on the physical plane, which is some normal in the physical plane, which we denote as some intersection point on the first octant sphere that we have drawn. Okay. So that finally concludes the study on the maximum and minimum stress values and the corresponding directions. Because remember that the idea was to find the maximum minimum stress values as well as the corresponding eigendirections. So we discussed a bit more. We talked about the directions corresponding to any arbitrary point on the stress plane. Now, the next discussion we have here is on plane stresses. So plane stress refers to a situation where one principal stress is 0. So what that would look like is if let's say you have sigma 3 as 0, so the way we had drawn earlier, sigma 3 being 0, that means that there's no normal stress in the x3 star direction, or the plane that corresponds to the x3 star direction. Now remember that we can choose a Cartesian axis in any arbitrary ways. So let us say that we had actually chosen the axis which looks like x1 prime and x2 prime, and the third direction was x3 star. So in that case, our stress tensor would look like sigma 1 1, sigma 1 2, right? Sigma 3 3 is 0. In fact, on the x3 direction, I mean, on the cutting plane, which is a normal in the x3 direction, all stresses are 0, because I mean, we already know it's a principal direction, so that means that it only has a normal component, but even that normal component is 0. So that means all these components are 0. Now x1 prime and x2 prime are the directions in the x1 and x2 directions. So there you will have a normal component and corresponding shear component. So you have sigma 1 1 as a normal component on x1 prime, and sigma 1 2 as the shear component on the x1 prime plane. I mean, examples of this are that if you have an unloaded point on the boundary of a surface, if you're talking about a loading on some surface, then if you have a point which has no external load, then what that means is that if you take this normal, which is the outward normal at this point P, then there is no stress in that direction. That is no normal stress, no shear stress. So that will come out to be equivalent to this x3 star direction. And then you can take the other two directions as any two directions, such that you make a right-handed coordinate system. So then you can write the sigma or the stress tensor using these three directions. Again, we will see later in the course that we'll use the idea of plane stresses. But right now, we just want to state the definition that plane stress is a situation where one of the principal stress values is 0. Now again, if you actually wrote sigma star, then of course you will get a diagonal matrix with sigma 1, sigma 1, sigma 2, and sigma star is the sigma seen from the principal coordinate system, that is x1 star, x2 star, and x3 star. And this is, we call it sigma prime because we're talking about x1 prime, x2 prime, and x3 prime. Again, I mean, if we draw the Mohr circles for this, now let's see if we can do it somewhere here. Then we say that exactly one of the principal stress values is 0. That is it's here, and the rest two are non-zero. So we can have any case. I mean, we can have the rest two lying both on the right hand side, or we can have the rest two lying on the left hand side. So if we take some arbitrary case that let's say that the two values lie here, that's your sigma 1, 2. So the situation we chose was that sigma 3 was 0. But of course, you can have a slightly different situation as well. So in this case, we have the Mohr circles, which look like this. Right. So the x1 star direction corresponds to this point, point A as we call it, and then we have point B, which is my x2 star direction, and then point C corresponds to my x3 star direction, which is 0 here. Now we're talking about x1 prime and x2 prime. So x1 prime and x2 prime are in a plane which, so x1 prime, for example, this x1 prime direction is on the plane that is perpendicular to x3 star. So that means that lies on the circle number 2, which is the small e to small b. So my x1 prime would correspond to some point here, and similarly x2 prime again lies in a plane which is perpendicular to x3 star. So that would lie somewhere on the same circle but on the opposite side. And the reason being because the angle between x1 prime and x2 prime is 90 degrees. And if you remember that we theta in the physical plane corresponds to an angle of 2 theta in the stress plane. So I will have my points, the blue points separated by 180 degrees. So I won't talk too much about this Mohr circles because it's simply an implementation of what we already have discussed in the previous discussion. I'm sorry, I'm just hurrying a bit because we have spent a lot of time on Mohr circles. So I really need to finish the discussion on stresses in today's lecture. All right, so that concludes our discussion on plane stress situation. Now the next discussion, which is extremely important in mechanics, is called the splitting of the stress tensor into a spherical and a deviatoric stress component. So again, these ideas that we are learning, we will be using them a lot in the future discussions when we actually start talking about the mechanics. So right now we're just talking about the stress or the forces acting at point P for different cutting planes. But we'll implement that rigorously later. And if something's not clear, just try to visualize it a bit. Again, as I said, Mohr circles are very intuitive. So if you just think about it a bit, then things will make sense. It's simply using the ideas of simple geometry, no advanced topics. Right. So spherical and deviatoric stress components. Now let's try to write the stress tensor. So this we'll call the spherical part, which I'll denote as, for now, let's call it alpha. And the deviatoric stress, we'll call it as S. Okay, so let's try to understand the first part, which is again extremely important, which is called the spherical part. Now let's think of why we call it the spherical part. What is the meaning of a sphere? Now the idea of sphere comes from a ball which we draw around the point P in this case. So sphere means symmetry. Symmetry in all directions. All directions are the same. So the idea of spherical stress here means that this stress will be isotropic. So let's write the words here. Spherical So when I say spherical, that means that if I take the eigenvalues of alpha, eigenvalues, then I will end up getting the same eigenvalues. All the eigenvalues will be the same. And if you remember our previous discussion, then we said that if all the eigenvalues are the same, that means all directions are eigendirections. Okay. That means you take any n hat and you write alpha dot n, and you end up getting something times n hat. Okay, that's the direction of eigendirections. And if you take alpha times n, you get nothing but the same direction, which is either elongated or compressed or flipped. So what we're saying is you take any n hat at point P, and that n hat will turn out to be an eigendirection. So that's called spherical symmetry. So the reason we use the spherical word in the spherical stress is because all directions are eigendirections. Now, if I again ask you that think of some second order tensor for which all eigenvalues are the same, then there's no other then there's no other tensor which is other than some scalar component of the Kronecker delta. Remember when we said that Kronecker delta is the only isotropic second order tensor. Okay. Whatever orthogonal transformation you do, it stays the same. That's exactly what we want to state here. That alpha, which is the spherical part of the spherical stress, you take any coordinate system or any n hat, and you will end up getting, you take any principal coordinate system or any coordinate system, and you will see that it transforms to itself. It's a spherical symmetry. It stays the same no matter whatever transform you do. Okay, so that's the motivation behind calling it a spherical stress. So the spherical part of sigma is defined as, now you can see that it's defined as some constant times delta ij. In this case, we define it as 1/3 of the sigma m. 1/3 of the trace of sigma. Okay, that is so remember that the trace of sigma is invariant. Okay, and we define Sij as sigma ij minus 1/3. So yeah, this has to be multiplied by delta. Since I'm already using delta, index I in delta, so I should use some other index. So I call it kk in this case. Okay. Now, if you think of fluid mechanics, then your pressure is, negative of the pressure is nothing but your sigma. This is also called sigma mean times delta Ij. So if anybody has studied fluid mechanics or is studying it, or will be studying it, then everybody actually knows about pressure because you already have learned that in your school. So pressure is so for fluid mechanics, this sigma m is minus p. So towards the end of this course, we'll actually do some discussion on fluid mechanics. There we'll see that it's the pressure which is the hydrostatic part of the hydrostatic pressure, which is the spherical part of the stress tensor. And again, I mean, try to recall when you learned about pressure. What you learned was that pressure acts equally in all directions. Right? So now we can understand what that means. So if I take a plane, a hypothetical plane, which has a normal n hat, what I would see is that the pressure will apply a force which is exactly in the normal direction but inwards. That's the reason we have a negative sign. So it only has a normal component, no shear component. Pressure cannot apply a shear force. It only applies a normal force. If you take a ball very deep into the ocean, you will see that the ball will tend to be compressed because pressure is applying a force which is on any plane or any point which is you take any tangent plane of the ball, it applies a force which is inwards to the center of the ball. It's a spherical ball we're talking about. Okay, so I mean, force is nothing but sigma dot n, the traction vector. So if you take alpha dot n, you will see that since alpha is nothing but something times delta Ij, so if you take that times n, you get sigma m, which is minus p times n. So it applies a force in the normal direction only. But we will talk a lot more about spherical stresses in fluid mechanics, particularly towards the end of this course. Right now, we're just trying to understand the definition of these terms. Okay, so as we said that the spherical part tends to either compress the body in fluids, or it could also extend the body if the force was tensile, but it cannot apply a shear force. It can only apply a normal force because by definition it is an isotropic, or it is applying only normal force because of the delta in it. That means that whatever shear force sigma is applying, all that effect is contained in a deviatoric part. So that is the reason we have, deviatoric stresses. That's the reason we split the stress tensor into two parts. So one part applies a purely normal or a compressive force, and the other part applies the shear force. So one part changes the volume of the body, and the other part changes the shape of the body. Again, I'm very loosely saying these terms. We will discuss more when we talk about the strains as to what it means by changing the volume mathematically and what it means by changing the shape mathematically. We'll quantify these words that I'm talking about. So we are almost out of time. So I want to stop here, as I've been seeing that I've been taking more than 50 minutes per lecture. We are only left with one small topic, which is on the octahedral shear stresses. I will just ask you to read that yourself from the book. It's only a couple of paragraphs to read. In the next class, we will start a fresh discussion, which is going to be on strains. So we have talked about stresses till now. The next discussion is how to quantify the kinematics, or the movement or the motion in the body because of the external stresses acting on the body. All right. Any questions? I have a couple of questions from the others. I'll read a few of them. So one question is the primed coordinate system arbitrary? I'm sorry, I missed this question earlier. I think it corresponds to this. The answer is yes. The prime coordinate system is arbitrary here. The reason being that we were just trying to find an arbitrary coordinate system in the x1 star, x2 star plane. Okay, so yes, it is arbitrary. And the other question is sigma s min is 0. That's correct. Now we said that sigma s min is the minimum value on the sigma s axis, but having a negative value of sigma s has no meaning. It simply means that it's acting in the opposite direction. Okay, so there's a difference between sigma n being negative and sigma s being negative. Now, again, if you're confused, just try to draw the stress tensor, the stress vector. Sorry, try to draw the traction vector, the stress vector, and see what it means by having a negative sigma s value. it will simply change the direction on the cutting plane. You will stay in the cutting plane, but you will end up getting in the opposite direction. But sigma n being negative actually means it's pointing inwards. It is changing the volume of the body. It's compressing the body. But sigma s being negative will simply change the shape of the body in the opposite direction. That's the reason we tend to take the modulus of the sigma s max or sigma s value. It's only the amount of sigma s that matters, not the direction. Well, direction matters, but not in terms of it being positive or negative. The other question I'm not answering, they're about Mohr circles. And again, as I said, that if you just spend some time with the circles using geometrical ideas, you will understand what they mean. Okay, if you're still confused about something, feel free to email them to me, the questions that you have, and I will definitely get back to you. Any other questions before we end? All right, since there's no question, so we'll stop here. Thank you.